Hello, hello. Welcome back to another 341 lecture. Today we're going to be talking about leftist heaps. Ooh. We're joined here by Jules, even though he's actually over there. He's joined over there. He's looking out the window. It's a beautiful day. I have a cat graphic tee on. Is that appropriate attire for teaching a college course? Typically, maybe not, but today, we're online. Yeah, we'll be fine. We'll be fine. All right, moving on. Let's get into today's topic. Today's topic, we're going to be focusing on boops. Just boops. That's what we're going to be focusing on. Just a boop. We're going to be talking about leftist heaps, which are all about boop. So why do we learn about heaps before? Well, aren't balanced binary tree search trees just as good? Well, actually, they are for InQ and DQ. If all we care about for priority queue is implementing InQ and DQ, then we could use like an AVL tree and we'd be fine. So why did we talk about heaps last time? Well, we talked about heaps because heaps also support the construct or heapify method, two names for the same thing, that takes an unsorted list of items not ordered by priority, they're just completely unordered, and you can put them into a heap you can construct a heap from them in linear time, which is faster than if you tried to insert n things into a AVL tree. It would take n log n rather than n. So heaps are more efficient at taking an unordered set of stuff and making them ordered very fast. So, what if we want to merge priority queues? How long does it take to merge two priority queues? Well, if we assume that their collective size is n, then we would just take every value out of the one heap, which would be one half n. We'd take one half n things and insert them into the other heap. So in our worst case, they'll both be the same size. So we'll have to do one half n log n insertions, meaning we'd have to do one half n log n operations. We get rid of the half because we don't care, and so it's n log n to merge. Well, today we're going to be talking about a heap that does it significantly faster. But before we get to it, we have to learn some more terms. Ooh. Uh, so leftist heaps have the same performance for InQ and DQ as balanced binary search trees and normal heaps. They also maintain the same heap property that the heap we talked about, the vanilla heap that we talked about last time, the original flavor heap last time. Uh, it has the same performance. So it has logarithmic performance for InQ and DQ. And it also maintains the same heap property as an original flavor heap. But this time, we're going to go back. We're going to stop representing trees as arrays, and we're going to go back to representing them as linked structures. So with left child, right child pointers. So the first concept we're going to talk about today is null path length. So we're going to define null path length is the length of the shortest path from the current node to a node without exactly two children. Meaning, what is the length of the shortest path to a null pointer, to a null child pointer, is another way of explaining this. The value is stored in the node itself. Oh, right. So each node in your tree will have a little NPL, null path length variable in it that will keep track of how far away that particular node is from a descendant that is a null pointer. And that'll be the shortest distance. So if I have a null pointer If my left child is a null pointer, then my null path length is 0. So, um, and if I have just one child, then my null path length is 0. If I have two children, then my null path length is going to be at least 1. How does this compare to height? How does this compare to height? We'll do a freeze. Do a freeze. Ah, ooh, that one was much more contemplative. Anyway, this will always be shorter than the height. It'll be either equal to or less than the height of the node. So height is always going to be larger on a node than its null path length. Why? Because the worst case for it would only be strictly equal if you are the root of a perfect tree, because all the null path lengths of your height will be there. If you take things out of a perfect tree, you'll get to a null pointer faster than if you had to go all the way down to the bottom of a perfect tree. Anyway, null path length and leftist heaps. So we're going to define a leftist heap as it's a heap, so it has the heap order property, where each node is going to be either larger or smaller than all of its descendants. A min heap, the root will be smaller than all of its descendants, and a max heap, it will be larger. So it has that property, and it also has this property. The left child of a node must have a null path length that is no smaller, so meaning less than or equal to, the right child's null path length. So what that's going to mean is that our leftist heaps are going to sag down to the left. They're going to be longer generally on the left than they are on the right. Right? So we've got the heap order. We've got the null path length constraint. And then at every node, the shortest path to a non-full node is along the rightmost path. Right? So if my nodes hang down from the right, or sorry, if I'm heavier on the left down here, then it's going to be easier to find a null pointer on the right-hand side, right? It's going to be easier if I use the right pointer to go down, I'm going to find a null pointer faster. So what that means is that our leftist heaps are deliberately unbalanced. It is deliberately leaning to the left. And so, why is this important? It's for the booping. So, it's for snuggling. So what we're doing is we're creating a tree, or a tree structure that is, let's go here. And then I'm going to use sophisticated future technology of, oh, Jules left. Oh, Jules is in the sun over here. Can't even see that now. All right, cool. We got Jules Cam back. So use this superior technology of MS Paint. So if we imagine the tree is like a blob, right? It's not going to be a normal tree blob. Well, actually, it's actually going to be kind of lima bean shaped almost. So what we'll have is something like this, kind of kidney shaped, right? Because it's going to hang down more to the left. What's nice about this shape though is that it's like a stackable shape, because I could put another similarly shaped thing inside of there, or similarly I could pack it inside of an even larger shape, and then it can be leftist heaps all the way down. It's kind of like if you imagine these are like fish. Rawr. And it's like the bigger fish always, there's always a bigger fish type thing. So what these heaps are designed for is that leftist hanging down property geometrically is in place so that I can fit stuff in on the right, right? On the right is where I'm going to insert all this stuff. So if I have the tree, it's kind of like brushing all the stuff in the tree to the right so I can, or sorry, to the left, so that I can fit something in on the right. And that's the idea of leftist heaps. And the reason that we use leftist heaps is because we want a fast merge operation. So to calculate the null path for each node, we look at how many nodes we need to traverse to get to an open node. So this 2 here at the root has to go 1 hop and 2 hops to find a null node. However, 8, which is different than the height, because the height of it would be 3, right? Uh it has to go 3 hops to get to a leaf. We're not talking about a leaf, we're talking about any null pointer at all, right? If this 15 weren't here, then my null path length would be 1, because I could get to a null pointer really, really fast over there. So there we go. So a heap node in a leftist heap is going to have the left child, the right child, the data for that node, and the null path length. All right, here we go. So now, here's the algorithm for merging a leftist heap. All right. So, what we've got here, is this big enough? I hope this is big enough. Okay, so what we've got here is merge. And so we're going to merge 2 nodes, right? And what that's going to do is it's going to give us 1 node as a result that's going to be the newly merged heap, leftist heap. So what we do is we say we have h1 and h2. If h1 is null, then return h2. So if one of the trees is non-existent, then we just return the other one. So that takes care of these 2 lines of code. This line of code here is saying if the actual value of the h1 is less than the other, call this auxiliary function with these 2 items in their normal order, otherwise swap them. So what this is effectively doing is making it so that when you come into merge 1, the item on the left is going to be the item with the smaller value. So it's going to be the new parent. So we know from this that this is a min leftist heap. And then the item on the second item is going to be the larger value, or the child. So if we look at the parent, we say, well, if my left child is null, then if the parent's left child is null, then I'll just stick the child there that I want to put them there. Otherwise, what I'm going to do is, if I'm the parent node, I'm going to call the merge operation on my child, on the child I want to add, and my current right child. So what it's going to do is it's going to say, all right, my right child is now going to be the result of merging this child I want to add with my current right child. So I'll do that merge operation. After the merge operation is complete, so that will give me a leftist heap on my right hand side. Now I ask my children, hey, which one of you has the lower null path length? If the lower null path length is on the right, right? Wait. Yeah, if the lower null path length is on the left, I don't have a leftist heap anymore. So the way I can fix that is just swap my 2 children. Now my null path length is going to be my right child's null path length plus 1, because if I know my children's null path length, mine is going to be 1 larger than the smaller of my children's null path length, which is different than height, which is you're the 1 higher than the max of your children. This is smaller of your children. So after this merge is called, I will now be a leftist heap, which means when I call this merge on my right child and the child I want to add in, what I'm going to get back is a correct leftist heap, and the root's null path length will be correct. So this is a recursive merge operation. Okay. So let's look at some examples. Actually, before we do the examples. Wait, did I already steal this one? All right. I think I already stole this one. If I did steal this one, we're gonna do another one. I'm gonna pause. Bam. All right, here's another would you rather. Would you rather become a were-possum? Turn into a possum every Tuesday night from dusk till dawn. Every Tuesday, you're a possum. You're a bit larger than the standard possum, but you're a possum. Once a week, or once a week, a beginner musician will follow you around playing their instrument as loud as possible for an hour. And there's so that's the would you rather. So I guess we'll freeze it. I'll do the freeze. I'll do like a mid quaff. I'll quaff through this freeze. Refreshing. All right. Mmm. Time to time to drink more bubbles so that I burp more. Okay. So what we're gonna do is we're gonna look at these two heaps. We have 22 and 1. Uh oh. And so what we're gonna do is we're gonna take this right child. So you might be wondering, well, why aren't you using those little chips that you usually do? Leftist heaps aren't really good for the board game, actually. They kind of it falls apart. So we're kind of done with the board game for the semester. And you might be thinking, yay, no more trees. Yeah, I think we're just done. Yeah, all right. So this is a smaller value. These are min trees, so it's going to be the new root. So what do we do? If I have a left child, I'll just take the other tree and pop it. If I have no left child, I'll put the other tree on my left. However, that's not the case. So what I'm going to do is I'm going to merge my right child 7 with this other tree here. So now we have the original tree held off to the side, and now this is the original thing we're going to merge with this thing. So then we ask which one has a smaller value. It's 7. Does it have a left child? Yeah. Does it have a right child? Yeah. Now make 7's right child the result of merging 25 and 22. All right, so now we have this allocated here, and I'm merging 25 and 22. So 25 is the larger value, which means that 22 is going to be the new root. It does have a left child, so I can't just stick this here. So I'm going to merge 25 with the right child of 22, which is null, so it just finishes. So now this is the result of my middlemost merge. And so what I'm going to do is the recursion's going to end. I need to update my null path length here. So there we go. It's up to 1. Excellent. And so now I have a leftist heap. Right? But I still have all these other nodes over here on the left. Or on the left. I have all these nodes on the left. But we have now come up with a leftist heap. Cool. So now we're going to like walk out of the recursion and look at 7 is waiting for a right child, right? So we're going to connect these two. Zip it back up. Boop. Okay. And so now we have so where are we at in the code? We have just finished. So we did 2 recursive calls. We finished the one innermost recursive call. Now we're in the second one where 7 is the root. Right? 7 is parent here and child is 22. Or actually child was 25, but it's been merged in now. So now we're saying the right child is equal to merge. That was the zipping back up operation. So what we have to do now is swap the children of 7 if their null path lengths are bad. But they're not. They're fine. They're both the same, so I'm good. And then I need to update 7's null path length to 2. Oh, I'm not in presentation mode. I have to update it to 2. Nice. Okay. So now we're going to zip this back up, which is again, the zipping operation is this like assignment here. So we did the recursive merge. The zipping is this situation here. So it gets zipped back up. Boop. Okay, now, do we swap the children? Yeah, this time we do. Why? Because it's a leftist heap, so the thing with the higher null path length should be on the left, right? We want it to look kind of like a kidney bean facing to the, like, opening up to the right. So we're going to flip these two. So we swap it. Now, now we're almost done. We have to update the null path length up here. So what do we update it to? 2, because it's one larger than the smaller of the two. So we're done. Okay? So that's an example of it. So that's the merge operation. We're not going to prove this. We're not going to prove that it's logarithmic, but the merge operation is logarithmic on the size of the two leftist heaps. So that merge operation is logarithmic. How do we implement InQ and DQ? So first off, how do we implement InQ? Freeze. All right. InQ, I'm just going to take the single item and the existing queue, and I'm just going to call merge on them. And that'll take log time. Nice. That's all you need to do. What about DQ? How do I DQ? Freeze. DQ is. I love those of you who are watching the recording just see me go. DQ is you remove the root and then you merge the two. You merge your left and right child, and you're done. That's it. So you just use merge. So the coding for this is not bad. I mean, you have the merge algorithm. The InQ and the DQ are pretty simple. So, and both of them are just log operations. So we're getting back to that log performance. Great. So what we have now is a cast of, we have multiple data structures that implement a single abstract data type. The abstract data type is the priority queue. Oh my gosh. Oh, look at him. He's so sleepy. He's such a sleepy boy. We should talk quietly. So we have multiple data structures that implement one abstract data type, just one abstract data type, which is the priority queue. The first data structure is the balanced binary search tree, and it gets us logarithmic performance for InQ and DQ, and we probably have it lying around because we used it for maths. However, if we want to be able to construct a priority queue from a list of values not sorted at all by priority, then we might choose a original flavor heap, which is the standard heap, right? Because that'll let us construct things in linear time rather than n log n time. Nice. However, if we don't really care about that construct operation, and we're still doing a priority queue type thing, but we have multiple priority queues that occasionally need to be merged together, right? So imagine, like, we use the airline example of there's a bunch of people milling around and then you heap them in to get onto the plane. Well, imagine, like, a plane breaks down and they get a bigger plane to take two flights and merge them together. If you want to have that efficient merge operation, you would use a leftist heap. Yeah. So that's all for today. I'm going to let Jules finish his nap, and I'll see you in the next video. Or you'll see me. Something like that.